Yeah, so last time we saw the notion of weakly F regular rings, and it is basically that. Oh, yeah, yeah. So last time we saw the notion of weakly F regular rings, and that is precisely when every ideal is tightly closed. And so, however, the property of being weakly F regular, or sorry, the property of ideal being tightly closed is not local. So some localization may not be tightly closed, and therefore some people study the notion of F regular rings in which every localization is tightly closed. And there is a famous counterexample which is polynomial ring in four variables by a certain ideal, and a certain ideal they say is not tightly closed under localization. And yeah, there is a theorem by Lubeznik in 1999. So a graded F finite ring is weakly F regular if and only if it is strongly or F regular. So today we'll study the notion of strongly F regular rings. And yeah, so I had proved one theorem or lemma before that, which was M primary ideals commute with localization and tight closure. So if ideal is M primary, then tight closure and localization commute. And if every M primary ideal is tightly closed, then every ideal is tightly closed. So this lemma was used to prove that being weakly F regular is a local property. Oh well, sorry, that's not true. Being F regular is a local property. And yeah, that's what we did last time. We proved the lemma, and I did not prove this that weakly F regular is a domain. And I may not prove it today also. But yeah.
Sorry, can you move to that statement one more time, the last page?
Yeah.
Oh, weakly F regular rings are
Is
domain.
a in fact it's a normal domain.
Okay, okay.
Yeah. So today I'll start with the notion of strongly F regular. I will prove that strongly F regular rings are domain. So that, and I will also prove strongly F regular rings are weakly F regular. So F finite ring R is strongly F regular if for all C in R 0 there exists E positive such that R2 F star R 1 going to F star C splits. Yeah, this is equivalent to there existing a morphism phi from F star R to R such that phi at F star C is 1. Well, yeah. So, so first of all, yeah, this is the definition. You see that R2 F, well, so in this definition, I can take C to be 1. So there will exist some E such that R2 F E star R F E splits. And one can prove, in fact, that if it splits for one E, it splits for all E, where one goes to F star 1.
Can you show
So
like if it splits for one E, why it splits for like some general whatever E you pick? I think I saw
uh,
that like once before. I completely forgot.
yeah, actually, I myself don't remember the proof. I just saw. I just
Okay.
assumed that as a fact. Yeah,
Okay.
I'll
Okay. All right.
I'll check that. Yeah.
Yeah. Yeah.
So yeah. So this means that R to FR, F star R, the Frobenius map splits, and so such rings are called F split, and therefore we have that this map is pure. This gives F is a pure map. So what does it mean for a map to be pure? So M to N phi is pure if for all, what can I use? K R module, M tensor K to N tensor K phi is injective. So such maps are called pure maps. And it's clear that if a map splits, then it is pure. And so what? So there is one more theorem which I would like to state. It
Oh,
states
so
that,
this map from M tensor K to N tensor K, that is it the same map phi or it is like phi tensor one, something like
oh yeah,
or
it's phi tensor
K.
one identity. Yeah,
And then is there any assumption on the map phi? Does it have to be injective or something?
it turns out to be injective because I can take K to be R.
Okay, okay, okay. Okay, all right.
Yeah.
So what is the involvement of F here? If we are saying it is F pure or something.
So if the map R to R, the Frobenius map is pure, then R is
Uh,
called
oh, okay, okay, okay.
F pure.
Oh, okay, okay. All right. Yeah. Thanks.
And yeah, so what I was trying to say, well, yeah, is what I wanted to say. So, so yeah, strongly F regular rings are F pure and in particular F split. Well, yeah, F split is stronger. So R F split and in particular F pure. Yeah, these are just definitions. They may require they may be required later. So I'll state and prove a theorem which states that strongly F regular rings, yeah, are domains. Well, strongly F regular local rings are domains. So, well, if we see that a strongly F regular ring is F pure, so the Frobenius map is injective. So the proof is F is injective.
Uh, Aditya.
Haha.
Does the F splitness imply F pure in strongly F regular rings?
It implies it in general. So
Why is
in
that?
fact, so suppose M to N splits, phi,
Ah,
then
okay, okay, okay. Yeah. Sorry. Yeah. Never mind. Yeah. That is the right. Yeah. Right inverse is there. That means it should be injective. Yeah.
yeah. So if the Frobenius map is injective, then R is reduced. This was done in the starting. So to prove that R is a domain, it's enough to show R has only one minimal prime. So yeah, I'll assume that. Let us assume P1 to Pn are minimal primes. Of R. And well, with n greater than equal to 2. Then by prime avoidance, or whatever you like, choose Fi in intersection Pj minus Pi j not equal to I. Then f1 plus dot 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 plus fn is not in any minimal prime of R because each fi avoids precisely one minimal prime, and we can get a elementary argument for this. But since this is in R0, by the definition of strongly F regular, there exists a E naught positive such that, well, yeah, so I will use this equivalent formulation, which was this. There exists a map from FER to R, which takes the value 1 somewhere. There exists a map from FE naught star R to R such that phi at this value summation Fi. Oh, well, yeah, this is not correct. I want to write. Oh, I can erase also. Phi at Fe star F1 plus dot 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 plus Fn is 1. So this implies 1 is phi Fe star F1 plus dot 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 plus phi Fe star Fn. But now we'll use the assumption that R is local. Since R is local, all of them cannot lie in the maximal ideal. Some phi Fe star Fj does not lie in M, and therefore it is a unit. So let U equal to phi Fe star Fj. And yeah, I can pick some other F. Also observe that Fi into Fj is 0 for j not equal to I. This is because Fi into Fj lies in all the minimal primes. But if R is reduced, the intersection of minimal primes is 0. In general, it is the radical of 0, but that is precisely 0. So yeah, I can choose such an I, suppose. So Fi into U I calculate. That is Fi phi Fi A star Fj. So this goes as phi Fe star Fi to the P to the E to Fj. But Fi Fj is 0, so this is 0. But this gives Fi is 0. That is a contradiction because Fi does not lie in Pi. So this proves that R is a domain. Yeah, and later we'll prove that being strongly F-regular is a local property. So if I take arbitrary strongly F-regular ring, then we can prove it is a domain because every localization is a domain. And what will happen if every localization is a domain? That the radical the intersection of minimal prime is 0 for every localization. Oh, okay, there's some argument involved. The intersection of all primes is radical of 0. Intersection of all primes at every localization is 0. Yeah, the intersection of all primes is 0. Yeah, okay, so this works.
Sorry, what you were trying to say at the end?
Actually, so I was thinking that suppose we try to remove the assumption that R is a local ring, can we still say that strongly irregular rings are a domain? And I was trying to give an argument which apparently doesn't work. So I was thinking like this: suppose the intersection of all primes is radical of 0. So yeah, so what I will prove just now is that I'll state it as a lemma now. R if finite, then R is strongly irregular if and only if RP is for all P. And suppose I prove this, then I was thinking that can I extend this theorem to arbitrary ring, which is not local? Uh,
Sorry if I misheard this, but being a domain is not a local property.
yes, yes, yes.
Yeah. So even regular rings need not be domains in general. They are reduced because reducedness is a local property. But being a
Oh,
domain is not a local property. In fact, yeah, if R is a domain, then R localized at every prime ideal, every multiplicatively closed set is a domain. But the converse is
okay.
not true. But in fact, in that case, you can have that R is a product of domains. So this is
Oh, yeah.
an result of Heisenberg. Yeah.
Yeah, product of domain does not satisfy this property. Yeah, okay. Thank you. So yeah, let me prove this then. So whatever I was thinking may not work. So first, let us assume that f is strongly irregular and try to prove that RP is strongly irregular. Yeah. So yeah, let's take. So in general, I don't know if well, I have seen this trick at some places, and I don't know if it is very popular. So let P1 to Pn be minimal primes. R. Yeah. So it is enough to show uh, yeah, for C in R0 such that C by 1 belongs to RP0, there exists E positive such that and phi, well, yeah, from Fe star RP to RP such that phi of Fe star C by 1 is 1 by 1. Yeah, so yeah. So there is one argument I think which came up last time also. Oh, what is happening? Oh, where is- Yeah, is my screen visible?
Yes.
Yeah. So, so the minimal primes of RP are a strictly smaller set than minimal primes of R. So if C lies in R0, it clearly lies in RP0, and the converse is not true. So, well, yeah, what we have to consider is C belonging to RP0. Then it may happen that C lies in some minimal primes, say equal to Pj, and does not lie in other. So what we can do is pick C1 in intersection data I equal to j plus 1 to n pi minus union of those I equal to 1 to j. This C1 and then C plus C1 by 1 is C by 1 and C plus C1 lies in R0. So this trick was used also in the lemma which we proved last time. And yeah, let us proceed. So we can assume that. So by this trick, and by the above argument, it is enough to find splittings when C lies in R0. But yeah, so since R is strongly F regular, there exists a map from, well, F or C, there will exist a E, let that be E. There exists this map. So there exists a splitting like this. And then we can just localize. So localize this map. To get the desired prop, to get the desired map. So I think the problem would have been trivial if we could just localize this directly and see RP0 and R0 were the same. But there is some small trick in which from which we can assume that C in fact lies in R0. Yeah. Okay. So now we can prove converse that RP is strongly F regular. What I'm writing. RP is strongly F regular for all P. We need to show R is. So what do we need to show? Given any C in R0, there exists T comma phi such that phi Fe star R to R and phi at Fe star C is 1. Yes. So yeah, what we can do is fix a prime P in spec R. Then for this P, C by 1 lies in RP0 and thus there exists E, I will write P here, constant such that phi from FEP star RP to RP and phi at FEP star C is 1. So, well, yeah, R is a finite. And thus, what do we have? Form. Basically, there's form tensor duality in some sense. The isomorphic to RP tensor the harm. So whatever, let me call this phi P. So what this gives is, so phi P is image of, or there is some corresponding of phi P with elements say R by S tensor. Yeah, suppose phi. And what is the map from RP tensor here? You just multiply the R phi by S. And yeah, so we can assume that. So what happens is phi P at FEP star C. This corresponds to R phi FE star C by S. And if this was 1, we can assume that, well, yeah, I can put R inside and take some other C also. Since this is 1, R cannot lie in minimal primes. So we can assume phi at Fe star C is S, which does not lie in P. But then what we do is I localize at S now. I look at this map. Look at the same map phi. So this splits. This splits because then I can divide by S, and then therefore I will get a element from here which I can map at 1. So there is a splitting. So what happens is, so this gives for each P a F. Well, how come this is S no? S outside P such that, well, yeah, but something happens. So what we are getting is spec R is covered by union of those DS. What spec R is quasi-compact. So since spec R is quasi-compact, we get spec R is finite union of those. And yeah, and for each SI, so for each SI, there exists EI positive such that there exists a map from RSI to FEI star RSI, which splits. So let me put it as phi splits. And yeah, I also have a certain restriction that phi I at 1 is FEI star C. So I'm not changing C. But then take E to be max EI. And observe that phi from R to FP star R, one goes to FP star C splits. Yeah. So I can leave this as an exercise. Let me do the next theorem. It's that F finite regular ring. F finite regular ring, regular in the normal sense, is strongly F regular. So yeah, let us prove this. Well, since being strongly irregular and regular both are local properties, so we may assume that. So since the properties are local, we may assume R is local. And then yeah, since the ring is regular, there are many things which we can do. So, well, yeah, by Kun's theorem, well, yeah, FER is free over R. And since R is a finite, this is finitely generated free over R.
F star
And oh yeah, sorry. Therefore, all others for any C in R0, we need to find a splitting. We claim that Fe star C is part of minimal basis for Fe star R for some E. Yeah, so proof. If not, then Fe star C, since the ring is regular, or sorry, local, we have lies in M times the module Fe star R, but this is M to the P to the E for all E. Otherwise, so Fe star C lies in M to the P to the E for all E. This implies that C lies in intersection of those things, which is 0. Well, yeah. Therefore, there exists E such that Fe star C is part of minimal basis. Or Fe star R, and then it is clear that R to Fe star R splits. Well, yeah, so this proves that F finite regular rings are strongly irregular. And yeah, so well, I have not proved that strongly irregular rings are weakly irregular, but that is also true that any ring for which such map splits, every ideal comes out to be tightly closed, and localization and tight closure commute. So these kinds of rings are very strong in some sense. And so let me state one more result. Yeah.
Localization and tightly closed, like tight closure commutes in this situation, not in general, right?
No, it does not commute in general. So for strongly F regular rings, it happens.
Yeah.
Yeah. And yeah, so some people try to study weakly F regular rings and then go to something else. Some people study regular rings, F regular rings. Some people only study strongly F regular rings. Yeah, but it is not known if all three are equivalent. There are some results which say that, but yeah, let me state one more theorem. And after that, I think we can stop. So let R be a finite. And strongly regular. And then R to S splits for all S finitely iterated over R. This is true for the Frobenius maps, but this somehow happens in general. Yeah, let me prove this. Or yeah, I can prove it next time because I
We
want
need
to.
some other hypothesis that
Ah,
S is, suppose the map is injective or something, because you could take the quotient map that won't split. What is this?
well, there is no assumption in the way it has been stated. Yeah, I think the
So
proof
m-
works.
maybe, okay, yeah. Uh, there is also a related result, which is that if uh, R is a subring of S and S is strongly F regular, then R is a direct summand of S. Like subrings of no. Okay, maybe. Yeah, let's see the proof. I think it's an inclusion or something, because otherwise it may not hold.
Yes. Yeah, because quotient need not split in general.
It won't split, not like.
Yeah. Yeah, let's check. So well, it is clear that it is enough to prove for every localization. Let this map be phi. So if phi p splits for all p, then phi splits. P instead of
So what is P?
P is a prime of R.
How do you get a map like that? Because, okay, so you're saying RP to SP. Okay, okay,
Yeah,
yeah.
yeah. RP to SP, yeah. But then I get to a situation like this. And since R is strongly F regular, so this is a domain. So now what we can do is need to get a splitting. But suppose I have a surjective map, SP mod some ideal, and I get a splitting like this. Yeah, one goes to one. Then I can say that, well, yeah, I claim that doing it in this situation is enough. why is this true? So suppose this is the projection map. Suppose I get a splitting like this, such that phi compose phi and this is psi, suppose. Psi of RP goes to SP, SP goes, yeah, this identity. Then yeah, this map, psi compose phi will give a map like this. So this is fine. I can further go to SP mod I and try to get a splitting. So can go to SP mod I for some I. So what we will do is go mod minimal primes. Go mod a minimal prime. Then in that case, this SP mod Pj becomes a domain. And therefore, since RP is a domain, so you get to a situation like this. So I'll write them as R2S and phi, where both of these things are domains. Therefore, this so S is torsion free over R. So there will always exist a map from R to S, such that at one is C, which is non-zero. Let's see some element of S. Oh, sorry, I'm not correct. What I can do? Yeah, so take no. So yeah, since S is torsion free, take C non. Yeah, let me erase. Yeah, there exists theta from S to R, such that theta at 1 is C. Or C is non-zero. Because S is torsion free over R. There will always exist such a map. And since R is strongly F regular, there exists E. Well, yeah, since R is a domain, C automatically does not lie in any of the minimal prime. So R to Fe star R sending 1 to Fe star C splits. So yeah, let us call this splitting psi. And this map is theta. So we have something like this R to S to the Frobenius. And here also you can take the Frobenius. And this is the induced map. Was the theta, this is Fe star theta. So this diagram commutes. So this sends 1 to Fe star 1. It sends wherever Fe star theta 1. Oh, theta of 0. Yeah, mistaking many things, but there is some map. Original map was 5. Therefore, this is 5, 1. But we also know that Fe star theta, which is a map from Fe star S to Fe star R, sends 1 to, well, Fe star 1 to Fe star C. So there exists a map like this. Suppose that is Fe star theta. So what we can look at is there exists a map from, so phi is from this. Okay, the splitting of psi. So I have a map like this, and I have a reverse map. Suppose this map is composition sum, Fe map. So I have a composition. So I have map from R to Fe star S, and I have a reverse map. So this sends 1 to Fe star 1, which is Fe star again 1 only, because this is a ring map. And Fe star 1 under Fe star theta goes to Fe star C, but Fe star C under psi goes to 1, so this is a splitting. So 1 loops back to 1, so this is a splitting. So this map splits R to Fe star S. But what do we have? R, S, Fe star S. Well, this was Fe star R. So if the composition of this map splits, we can claim that R to S also splits. So how is the inverse thought of? 1 goes to 1 under this loop. So I can just follow this path, this long path, as this diagram is commutative. This long one gives a splitting of this. So R to S splits. Now let us try to do this for column integration, because this sounds, well, some chart has come. Oh, okay. I made you once you're done. Okay. Yeah, thank you. This, yeah, let us take polynomial ring only. And so polynomial rings are strongly F regular. I can take this. Suppose I go to mod x square. This doesn't split, I claimed. Let us check. This is obviously module finite. But what they do is, so our next step was to go to FP. And FP to FPX, there is some splitting. And this sends 1 to 1 overall.
Yeah,
Oh,
but
so I,
the issue I think is that FP to FPX is as an FP module, but why does the composite have to be FP mod X square module? You know?
yes. So that is the issue.
Yeah.
Yeah, so I think there must be some subtlety in the proof, or yeah. So, I think this map doesn't split. So we should check this. Doesn't
I don't
split.
I don't know if this is the correct result, but if you have a direct summand of a polynomial ring, I think it must be co-Macaulay or something. I'm not sure if this is true, but there are
Yeah,
uh
I think that is true.
yeah, so if you look at a polynomial ring, so you can't expect that every quotient of polynomial ring is co-Macaulay.
Yeah,
Yeah.
yeah. Yeah, so I think this result is not true. And so yeah, this step itself is the problem. That why is the composite injective, or there are several problems. So I'll check this. I think this is not correct as of now. I wanted to
Uh,
do one. Uh-huh.
uh, yeah, so there's also this result, right? If R inside S is a direct sum and R is a direct sum of S and S is strongly F regular, then R is also strongly F regular.
Yes, yes, yes.
Oh.
Yeah, that is true. And FP mod x square is not, right? FP x mod x square. Like
Yeah,
in
it's
general,
it's not it's not there.
because it's not a
Well,
domain. Yeah.
it's a local ring, but not a domain.
Yeah. Okay. So I wanted to do an exercise. Somehow I like this. Yeah, office the time it's 10:05. So the thing is, yeah, R is a finite. And M is finitely iterated over R. Suppose there exists M in M such that R2 FP naught star M 1 2 FP naught star M splits for some finite element module, then R is F pure and R2 FEM 1 2 FE star M splits for all E greater than equal to E naught. Yeah. This is a very nice exercise. It's there in Lynch on Thomas Polstra book. Um, so yeah, I'll try to solve it. The way I saw it was that since there is a surjection from sum of R to M, and there is a map like this, and one going to M. Since this is projective, this extends, and then we can yeah. So I was not able to complete this. Or wait, so what or what happened? So we know that there is a splitting from R to FE not M, but there is a surjective map like this, FE not star R to the direct sum of these modules. And suppose one goes to, well, we know if we, and I can take a pre-image. Suppose that is the vector x. So I can define a map from here to here. And I claim that this will give a splitting. So I claim that x is part of minimal basis. Yeah, so this part I was not able to prove, but I assumed this, suppose. Then what will happen is that R2 F E naught star R direct sum n. Since x is is part of a minimal basis, I get a map like this. Where x goes to E1. And since this was a splitting, I can just compose with inverse of this and go like this. So I can get a splitting like this, where one goes to E1. But in that case, I can get a splitting like this. I get a splitting like this, where one goes to 1. Well, if E star, if E naught star 1, this splits. But yeah, this implies R is F split. And therefore R F pure. And yeah, so, but I am not sure about this part, that this X part of minimal basis. So I thought that maybe
And you
one of
don't
you
need
have.
all of this.
Oh, so is there some very simple way?
You can decompose. So R to Fe star M. Put an Fe star R in between. So
Yeah,
write the composite now. R to Fe star R to Fe star M.
yeah, R to F star R to F star M.
Where one is taken to one and one Fe star one and one Fe star one is taken to Fe star M.
Yeah,
So this
so
is, and this composite is the map that we have.
yes.
Okay. And the composite splits, therefore you can get a splitting from Fe star R to R.
Oh yeah.
So R splits it. Fe splits.
Yeah, okay, this is much simpler. Yeah,
You don't need all the generators and all.
okay. And then yeah, so yeah, I was stuck on that part. I think now this can be continued. So other parts do not seem to be that hard. Still I have not done, but I think I
What do
have.
you mean other parts?
So we need to prove R is F pure is clear, but why does this map split for all E? That is something which we need
Oh,
to
so
show.
one, if R to Fe naught star R splits, then R to Fe star R splits for all E greater than or equal to E naught. That is also like you can have a composite like R to F E naught star R to F E minus E naught star R, and then uh, yeah, I think it's there in
Yeah.
it's there in the De Stefani notes. where
Hmm.
in a split section they talk about this. If you find an E naught where it splits, then it must split for all E. In fact, not just E greater than or equal to E naught, for all E.
Yes,
So
yes.
yeah, yeah, yeah.
And yeah, so this map splits this thing. Yeah. I think yeah, I will check this. I just wanted to mention this so that I can get some help.
Okay.
Yeah, I'll stop screen sharing and I have a class, so I'll have to leave. I'm very sorry.
No,
Yeah,
no, take care.
so